Okay. Hi, everybody. In this lecture, I shall give you an example and illustrate this example where we find the minimum of a nonlinear function with single variable by using LabVIEW. But before working with this example, I want to give you a general idea about LabVIEW itself. As you see here, we have two pages. This white page where the code is given, and the other page where we have the inputs and outputs of the program or of the code. Concerning optimization, really, LabVIEW has a very rich library. To go to this library, right-click here and select mathematics. Now you go to this subpalette of mathematics where there is optimization. This palette of optimizations has a subpalette of different functions which may be used upon desire. As you see here, this is linear programming function, for example, or quadratic programming virtual instrument, Brent method with derivatives, one-dimensional array, VIs, find all minimums for one-dimensional VI, or all minima for n-dimensional VI, and a lot of them. Each of these functions has a sufficient detailed information which you can refer to. For example, today we are going to work with the Brent with derivatives 1D VI, one-dimensional VI. In order to know more about this function, you can right-click the function and press on the help. Then you will have a new page, as you see here, illustrating the inputs which are to the right side, usually, and the outputs which are at the left side. You have the inputs, and at the right side you have the outputs. For this specific function, at the right side you have an input here called formula. If you do not know what does it mean, you can read what is given downwards here. Formula is a string describing the function under investigation. The formula can contain any number of valid variables. So you need to give the formula which you are going, or the function, the formula which describes the function which you are going to find a minimum for it. Another inputs here at the left side is the start point, and A, it is called A, and the end point, which is C, and a middle point, which is called B. These points are related to the function and must be within the range of the function. The accuracy input, of course, it is written here. A, for example, is the left point of the bracketing interval. The default value is 0, 0. B is the middle point, and C is the right point. Default values are 0, 0. Of course, you have to put your own values. We will see through the example. The input from here represents the accuracy of work. This function uses the first derivative, and of course, you know, this includes an iterative process also. And the accuracy of calculation here is defined through this input here. You give the value you want, but the program itself suggests for you the normally used accuracy value. So this input here controls the accuracy of the determined minimum of the formula. And also the method stops if two successive approximations differ not more than the value of the accuracy. So the accuracy here, in another way, it is the value which is acceptable by you as an error. It is a tolerance value of the solution. At the output here, you get the value of the minimum of the function, if minimum here, and you get the coordinate value where minimum occurs here. If you want to add this icon to the block diagram, you just click on it and you go and put it on the block diagram, and it will be there, and then you'll work with it. I have already worked with it. It is here, so this is not needed now for me. Just I wanted to show you. Now, anyhow, maybe it is good to show you how this is the mathematics optimization. This is the Brent with derivative 1di. If I put the icon here, as you see, this input, which represents the accuracy or the tolerance, I can right-click it here and create a constant value which represents the acceptable accuracy. Here it is, as you see, an exponent of -8, which is very low value, very, very low value, which means very high accuracy is given. But you can change it. You can write it when this is for exponent, when to the exponent of -6 or -7 or -5. It depends. But the program suggests you for this function, and for most of the functions, really, the tolerance value is suggested directly by the system. So you do not need to work with it. How these are drawn, it is not that difficult. If you want to see, anyhow, if you want to see the connections here, you can also press here on the help and show, and press and show context help. You will see this figure here, where the outputs are shown, the minimum and the f of minimum and the number of ticks and the start and so on. Okay, so I put the cursor here and right-click it and write create indicator. This indicator now is the minimum. It is given here a name minimum 2 because in this block diagram we have already one minimum before, which is here. This icon could be minimized, as you see, to view it as an icon as I do here, so that the drawing is not confusing and neatly done, clear for you. Here the other output also, I right-click it and press create indicator. I have another indicator which represents the F minimum. It is F minimum 2 also because we have another one before. Of course, the same thing applies for other values. For example, the initial value here, not indicator, I want to have maybe a constant or a control as I want. If I want as a constant, I just press the constant and I have a terminal here and I fill it with the value I want. I keep it as 0 because it is the initial value and normally this function begins with 0, so I keep it as 0. Of course, I can change it to any other value like 1 or 2 or 3, as you see. The middle value be also create a constant and I fill it with another value. And the third value is also as a constant and I fill it with the appropriate value. Of course, you can change these values here. If you write here, for example, 7, you can, and this is, for example, 89. So you can change this number 89, for example, again to 6 upon request as you want. But you can do this also by supplying, as you see, this line represents that this is not necessary. You have to get rid of it. So I go to the edit menu and press on remove broken wires. They're gone. They are gone. I can here indeed ask to create a control. So I have the same thing, but I cannot make the input from here. I have to go now to the block diagram, a start. Here it is, a start. And I input here the value I want. Suppose I want number 76, so this is the input. Now this value which is here is inputted here. It is called a control, and now any change, of course, there is a possibility to increment this value, to increase it by ones or decrease it by ones, and so on. It depends really what do you want, which is better for you, but for me it is equivalent. There is no difference, no serious difference. Okay, now the other interesting thing is to create the formula which we need, which should include the function which we are going to work with. I right-click it here and press create constant. And this is now pink color represents that here the input is a string. As you see, it is a string. Before work, this string, of course, should include the formula which is here. I have to write, I will show you a little bit later how. I can expand it and write here inside it the required text which I want. Really what I have done here, as you see, I have included an element which is called concatenating of strings or concatenate strings. So the components of the formula are input here as a sequence, and at the output I will get the concatenated string. If I press here, I see here, this is the result, which is the concatenated string, which is x squared minus 4 multiplied by x plus 3. So what I have here, which is in this line, which feeds the function, is now including this mathematical expression, which represents the function which I am going to find a minimum for it. Of course, the data in this line here is the same data which is at the output of the concatenating a string, or the same output which is shown here to the left. In order to work with this concatenating function, this is really always done by strings, related to strings. So I go to the string palette, here is a string palette, and you see concatenate strings. So I press it and put it here now. And now I expand it as I want. And now I begin including the variables or the information which I need. For example, here I create a constant and I call it 6. The second terminal, I create a constant, minus, I put a minus here. I want, for example, 6 minus another value, which is, for example, x. So when I run this program, in the program, I'll get the output here. I create an indicator, and now this indicator will include a value which is 6 minus x here, and the output. If I go here and run, let me shift it a little bit, and I run both programs. Of course, I cannot run them because there are many terminals which are not connected. This must be removed. And where else also? Here there is an error message. Concatenated strings. Oh, okay. The idea here, the concatenating string function is not completely filled. It must be closed now. Now, no, not yet. And now it is okay. So this, as you see, arrow now is continuous. There is no break through it. So the program is okay and nothing wrong. If I run the program now, I shall get here at the output here, this value 6 minus x, 6 minus x. Now this value, which is resulting here, I can take it from here and connect it to another function. This upon request, for example, I have another function here and I want to introduce this value to the function. So I connect it with it. Now this value which is here, which is 6 minus x, now is fed to this function. Okay, I hope that this is clear for you. As a beginning, I shall try to explain every time the information I feel it necessary for you. So for this function, as you see at the input here, I included a value 0. The function, if x equals to 0, will have a value of 3. So we can conclude that this value here must be 3 and not 5. I put it 3, for example. 3, and this value in between. So there is no rule for that. It is a middle value. You can take the square root between 0 and of 3, for example, or you can put 2 or 2.5 or 1.5. Any of them is working. It works, no problem. So these three inputs, the start and the middle value, the bracket, and the end right value are included. What is the function here? It is x squared minus 4x plus 3. If you go here, you see here x squared, it is input to this terminal. The second terminal is minus. The following one is 4. The following one is multiplication element, multiply by 6, add to that 3. In this sequence, these elements in the string are concatenated and given as the output as a formula, which is fed to our function. So I think it is now clear how we work with it. Now, why I selected the Brent with derivatives to work with? Because this is the same function as minimize scalar, which we used in the previous lecture for minimizing the function, which is as written here, x squared minus 6x plus 5. This function is the same type as the function which I'm working with now, which is x squared minus 4x plus 3. Instead of 3, we have 5. Instead of 4, we have 6. And x squared here, the same as square here. So the same type of function we have here. This function we worked with in the previous lecture. So now, after demonstrating to you this function, I will work with it to show you the results. Now we have the function x squared minus 4x plus 3. If I run the program, the result, of course, is shown here. But if I run the program, I will have the same result. So the minimum value of this function will be 2. And 2 here is the x value, the coordinate x value at which the function has its minimum. The minimum value f of 2 gives you minus 1, which is the minimum value of the function. Now, suppose we want to work with our function, so we need to change x squared, it will be the same, minus, it is the same, it is still there, the second position. 4, we will change it to 6, so here we write 6. And, sorry, 6. Now, this 6 must be multiplied by x. This is the multiplication string is already existing. X is already existing, no change. Plus 5, plus already exists. Instead of 3 here, we have to write 5. Now, I suppose that at the output here, we have the function x squared minus 6x plus 5. And with this now, if we consider the inputs here, the input at the beginning 0 is 0. When 0, it is here 5 instead of 3. So I have to write here 5. This is the limit value. And I think the program now is okay. Now, if we run the program here, these values will change accordingly. And you remember in the previous lecture that really we have found that the x value was equal to 3 and the value of the function was equal to minus 4. You can refer to it to be sure that we have got the same answer. So why I have begun this program at this lecture, I wanted to give you, first of all, a quick briefing about LabVIEW environment and how we work with LabVIEW for minimization of functions. Because now we shall continue our work using the derivatives and extracting the derivatives of the functions for the sake of finding their minimums. So I will go out from this page, and now I shall open Python notebook, and there we will begin learning with or optimizing by using the derivatives. Okay, so with this I have finished. Don't save. And this is not needed also. This is also not needed. So we go now to Python. I will go to open my notebook. It will take half a minute maybe. Jupyter. Sorry. Jupyter Notebook Classic. Enter. Again, Jupyter Notebook Classic. Enter. It is open. Okay. My notebook has opened. I want to go to the folder where my program is existing. Now I open it. It is opened. Let me expand it. Now we are here. You remember this function which I have talked about, which is x squared minus 6x plus 5. We have found its value of the function is minus 4, and the value of the coordinates was 3, and we have solved this using 3 different ways. We have drawn or plotted the function, and we have overlaid there the value where is the minimum. All these things now you have it, and we have done it before. But why derivation, and why we have to know how to use it in minimization processes? I have told you, I think, also that the major 2 groups of optimization are either by using derivatives of the function, first order derivative and second order derivative sometimes, or by using the iterative processes. So derivative processes is essential, and we have to know about it. So in this lecture also, now I shall try to show you how we can get the derivative, find the derivative values at different points of a given function. When we talk about the derivative, you remember it is the limit of delta y relative to delta x, where delta x is approaching a zero value. So we are talking about a derivation in a point. So this in Python is done by having the limit of the function f of x, but with a displacement equal to h, and this h displacement is very small and approaching zero, minus f of x, and all divided by the displacement x. This gives you the derivative of x. Also, really, we can use a more precise expression, which is called the central difference formula, where the derivation also, or the derivative, is equal to the function of x plus displacement h, where h is a very small value, approaching zero, minus f of x minus h. Again, h here is the same as h here, and all are divided by 2h. Applying this function, we can find the derivative at each point x of any function. Let us try to do that. So in order to do that, we have to know the function, and we have to know the points, the x points, the x coordinates of the function at which we want to find the derivatives. So at first, we import numpy, and we call it np. We will work now with np instead of writing always numpy. And in order to plot the function and in order to plot the derivative function, we need matplotlib library. So we import matplot library or lib pyplot as plt. Now we will work with it as an alias plt. We do not need more packages or libraries to work with. And now we need to define our function. We will use our same function, x squared minus 6x plus 5. So we define our function with a name given f, this is the name, and a variable called x, which is here included. This is the definition of the function. Now, x itself, which represents the values of the x values in the horizontal line, is practically an array. So we call numpy np, we call it, and through it we call a linspace function. I told you about it a little bit. This linspace function requires the limits of the x value. I will take between minus 20 and 20, and this range will be divided to 100 equal values. So we are talking about 100 values of x between minus 20 to 20. This is assigned to the variable x. So again, x is now an array of values. Of course, I can print it and show you that really it is that. And if I want to, if I write here print, let me say to you print array, for example, prime array equal array. And now I will run the program. I shall have an array of values of x, which is called an array. So run it. There is something wrong here. Print array and array. Name array is not defined. where it is not defined. Ah, here I am, the array itself, which was created, was given a name X. So instead of array, I have to write here X, print X, and here instead of array X, and now it will give me the values. So as you see here, we have 100 values of X, beginning from -20. Here is, where is the -20? At the beginning here, -20 up to 20. So beginning from -20, -19, -19, and so on, so on, so on, coming higher, higher up to 0. You come up, this is 1, this is the 0.6, 0.2, it's about 0 values. And now they become they are minus, all of these are minus up to a given value, then it becomes positive and increases up to 20, 18, 19, 20. So these are the values, all these values are of X, which means we have already created an array of values. So I do not need it in further work now. I will stop, exclude it from the program. Now it is excluded by typing this hash here. So we have created the array of the values of X. In order for the formula to work, I told you we need to define the value of H, which is the displacement which is taken, and it is very small and very near to 0. So it is taken here about 0.01, this is X. And now here is our function. So we now have X, it is defined, H is defined. The function f is also defined, we know it. So this formula now is already defined. We assign it, this formula now, which will calculate the derivatives at each point of x, is assigned to a variable. We call it calculation derivative. So now this variable calculation derivative includes all the values of the derivatives for all the x values which were of the function, I mean values relative to each of these x values which are included in the array. So this derivative, calculated derivative, now is included, and for each x value here, we have a function value. For this value, we have a function value. We now, for each function value, which is relative to each of these x values, we have a derivative value. This is the derivative array, or array of derivative values, which we will get. It is from -46 and becomes to -45, -44, -43, up to a value around 0. Here it is -0.7. Now it is 0.6. So it is positive now. And now it becomes increasing up to a value equal to 34. All these values are the derivative values corresponding to each of the x values which exist in this array. If we look at I have drawn it, plotted it. If we look at the graph, I will explain to you how we found it. So this graph, this line here, represents the derivatives for each value of x beginning from x minus 20 up to x equal to 20. If you note, this is the ordinate. This is the 0 level. So the derivatives are minus. From -20, they are minus and became positive only after 0. This is the 0 level. After 0, after this point here, they became more and more positive. So the derivative at one side before the zero, it is negative. After the zero, it is positive. Why? If we look at the function here, here is the function which we have drawn in the previous lecture. And really, if you remember, we found that the minimum occurs at the value of 3. Here 0, here 5, 3 is approximately here. So as you see, here is the minimum value of the function. And the minimum function value of any function occurs where the derivative is equal to 0. So this is the 0 value of the derivative. In this part, where the derivations or derivatives are positive, as you see, at each point here, the derivative is positive until you reach the 0 value of the derivative, and then the derivative becomes negative, which is for this side of the function. So the derivative of derivations or differentials have a maximum value here, and they become to decrease and decrease and decrease until it is 0, and then it continue decreasing as positive, as negative values up to the value of -20. Now let us go back to our function. So we have now the expression of the, to find the derivations, which is called a variable called calculate derivatives, and now we have seen that they really exist. So in order to see them, I have printed them. I said print calculate derivatives, cal derivative. Note here that in Python, the names cannot be written continuously. You need to always underscore between every successive two values or two names here. Or you can write them continuously, but the value C, ALC must be capital and D must be capital. The most common way to express that in Python is to write as you want, but with a space here with underscore sign. So now we have printed all the derivatives. Now, what else? Really, I have tried to show you some specific moments which are very interesting for you. The first of all, I am trying to work with you to find the minimum value here. If you want to find the minimum value of the function, of course, you need in advance to know the minimum value or the value of the coordinate at which this happens, which is 3 here. But how to know it is 3? I know it is 3 only if I look at the graph. But this will be approximately 3 because I do not exactly know it is 3 or 3.1 or 3.05. I don't know. So how to find this x exactly here? I can know it only by knowing the derivative, because I know exactly the derivative is equal to 0 at this point. So I have tried to explain to you how I am thinking and how you have to think. Because the array, which is now resulting of the derivatives, has a positive part and a negative part, so I have to work with the absolute values. I cannot work with the negative and positive. If I can ask the minimum value, if I go to the table here, calculated derivatives, you see the value, the minimum value because this is a discrete values, it is not exactly 0. The minimum value is from minus 1.5 to minus 0.7, and then it jumps to positive 0.6. The 0 value is not shown. This means that you have to add a high number, a large number of points instead of 100, maybe they have to be 1,000, so that you get a very small value here. And even this very small value, you cannot deal with it with arrays. I will show you now why. So, first of all, I have to find or to convert this array of derivatives to an absolute values. Absolute of calculated derivatives, I call it SAMI, for example. Now we have a new array with a name SAMI, but it is with the absolute values. There is no positive and negative. Only you deal with the positive values. Okay, so now we have, I print, for example, I ask the program to print the minimum value of SAMI. Because this is a NumPy array, so NP dot minimum function of the array SAMI. Now it will give me a value. So SAMI as a minimum value now here it is. It is not as shown here, 0.6, sorry, where it is. 0 up to here 1.2, 3, 4, 5, 6, 7, 8. 8 positions, but now it is given exactly about 16 positions, 0.6, 0.6, 0.6, 0.6, 0.6, up to 43. This is the exact value of the minimum which I can take. It is called SAMI. Now for this value, I want to find the minimum of the function itself. Every value in the array has an index which represents its position there. So this value minus 20 with an index 0, and this value with an index 1, and this value with an index 2. So what is the index of this value, which is, let me say, 0.6, well, this value, 0.6, 0.6, 0.6, 0.6. What is the index? I don't know. If the number is, let me say, 500, I have to begin counting from 0 until I go and find the index of this value. This is a troublesome and annoying thing. How we can define the index of a value of the array, of NP array, and dimensional array, and not why? Because this is not, as some of you may expect, that it is a list. This is not a list. This is an array. So how to do that? I am trying to show you how to do it. So now we have the exact value of SAMI. This is the exact value. So what I ask, I go to NumPy and use the where function. In the where function, I include the variable calculate derivative equal to this value. So the calculated derivative, which is equal to this value, okay, I give it a name called Ali, and I want to find Ali. So this Ali now will give me the index of this value. If I write 0.6, 0.6, 0.6, 0.6 up to this point, I will not get the answer. I will get nothing. This is the problem. So if I go down now and I look, I find that Ali, it is an array with an index 57. So the index of this value, of this value now is 57. I know the index exactly now. If I know the index exactly, I can know the value of the function through the index value. So now I know Ali. What does it mean? I have printed it. Now, if I know the value, if minimum of the function, so I can print it and it will give me the value which is -4. Another way to do that is to write, as you see here, to go to the NumPy library and directly ask the minimum of the function. The function which is here at the same beginning. I have the function. I can find the one without trying to find it through the derivative value. So as you see, NumPy dot minimum of f of x, I know f of x, so I can get the value f minimum, which is f minimum here, which is equal to -3.999, which is -4, as we found before. Anyhow, I hope that this discussion is useful to you and gives you the tie between the derivatives and the minimum value of the derivative, the signs of the derivative as positive and negative, how the derivative values decrease while approaching from the initial point of iteration up to the minimum value of the function. And here, really, it becomes equal to 0, the derivative. Why? Because the tangent to the function here in blue will be parallel to the x-axis. So the angle is equal to 0, and the tangents of the angle is equal to 0. Okay. In this lecture also, I will try to give you a briefing about some useful and interesting approach to find the derivative analytically. You do not need to think how to find the expression of the derivative. There is a special library in Python called SymPy library, which is used to calculate the derivatives. I shall illustrate with you 2 or 3 examples to be familiar with this. So suppose that we have a function already defined, f of x, which is equal to x cubic minus 2x squared plus 3.x minus 1. This is a function, and it is a continuous function. And we want to find the expression of the derivative. We shall use SymPy library. So we import SymPy as sy. Of course, you call it sy, or you call it sp, or you call it sk, as you want. But usually, if you accustom yourself to shorten the names, it is better. The program becomes more compact and you can remember it. So it is here shortened as sy, and you will work with sy as if it is SymPy. The first step to do is to call the function symbol, sy dot symbol, and the argument there is the variable here, which is x. And we assign this, the result, to a variable called x. Now we shall have the derivative. To have the derivative, we shall define the function for it. It is given a name h of x. Of course, it could be k of x, or s of x, or r of any letter. Commonly, H is used, as you remember in the equation there, also H was used. Here H is used. Anyhow, so define H of X as Sy, the derivative, the differential of f of x, which is this function, with the variables by x. And differentiate f of x by x. Sy differentiate f of x by x. This is the expression which will define the derivative. And that's it. Then you will print h of x and it will give you this expression. Now this expression really is the expression of the derivative of this function. It is here 3, so it becomes 3x squared minus 2 by 2, 4x plus 3, and that's it. Another example. Suppose we have this example where the function is called f and it returns s. This is our traditional example, x squared minus 6x plus 5. So at first we import SymPy as sy. Then we call the symbol function of x and assign it to a variable called x. And then we define the derivative. Now instead of h, I use the derivative of x, which returns a function which is sy dot differential of f of x by x. And now it will be 2x minus 6. Okay, if you are interested to know how we can derive the analytical expression of the derivation for partial derivatives, where the function is a function of more than one variable. So this is the general formula, for example, which we have. F of xy equal to x cubic minus 2x squared plus 3xy minus 1. So we have two variables, x and y. Now we should take the derivative of the function f of x by x and consider y constant, and take the derivative of the function f of xy by y and consider x constant. So this is the idea. At first we import the library SymPy as sy. Now we assign variables. So we call the symbol function of x and assign it to x. The symbol function of y, we assign it to y. And now we define our function. This is our function external to the program. Now we are defining it within the program. And then now we have to find two functions of the derivatives. The first function, for example, g of xy, which represents the derivation or the differentiation of f xy by x, and the derivation h of x of the function f of x by y. And then you print now g of xy and h of xy. G of xy and h of xy. You print both, you will get the answers downwards. This expression now becomes 3x squared minus 4, sorry, here by y we do not work, by x we work, so minus 3y minus or plus 3y, and here we now work with the y 2 by 2, 4, so 4y, and here y 3x are constant, 3x minus 4y. So as you see, I think that this is also useful in this aspect to know how we can work with the SymPy library in order to carry out the first derivative of the function and the partial derivatives of the function. Of course, if you want to take the second derivative, you only take the expression which results from the first derivative and make again a derivative action for it. So you will get the second derivative. Usually in the machine learning, we work with the first derivative and occasionally with the second derivative, but we do not work with higher order derivatives. I think now with this work, you have a good background concerning the LabVIEW and concerning the derivative or derivation by using SciPy, and how we find also the derivatives of all points of a given function and how to investigate this curve and how it is related to the original function. Okay, in the next lecture, I shall try to begin also with LabVIEW to show you how we can really also calculate the derivatives by using LabVIEW for the same example which we have solved just now. As I told you before, I am trying to solve every question, every example in Python and in LabVIEW so that you can compare between the results and maybe you will be in favor of maybe LabVIEW or in favor of Python in your future work. Okay, thank you for listening and goodbye.